Okay, so what are the important steps in MD simulation? So, to start your simulation, the first thing you have to know is a starting microstate. You have to start from some point. What is that point? So, you can choose a random microstate. So, when we mean the microstate of our classical system, we basically look at the distribution of particles or the atoms, or basically you have to know x, y, z coordinates of each of the atom that make the system. So, if it is a biological system, let's say your protein or DNA, you if you're lucky, then you might have a structure of your biomolecule available in something called protein data bank. So, as you know, the protein data bank has a lot of X-ray or NMR structure of various proteins. So, you can go to protein data bank and search for its PDB, search for its coordinates. So, if you are lucky, so you get the X-ray structure or the NMR structures, and from there you get the coordinates. So that is your starting structure of the protein. So, you can start from there, and from there you start your computer simulation, and that will generate you different microstates over time. If your system of interest doesn't have a initial coordinate, does not have X-ray structure or NMR structure, then you can, as I said, that you can make the coordinates a rough coordinate by modeling. So, you just have to make a approximate structure of the system, and then you are ready to go. You are set to go from there. From there, you will carry out computer simulation, and simulation will basically iterate over to get a better and better conformation of your molecule of interest. So, as I said, that the initial coordinates you can get from protein data bank. So, at the moment there are more than 80,000 experimentally determined protein structures available in protein data bank. So, in the protein data bank you can search here with the PDB ID. So, each of the deposited protein has a ID given by the bank, by this protein data bank. So, you can either search with the PDB ID, or you can, if you don't know the PDB ID of that particular protein of interest, then you can also search by a keyword. But the problem of keyword is, if you just say HIV protease, then for HIV protease there are about 600, 700 structures, all the structures will come. But if you want one particular structure, give that one ABC, and that will, with that PDB ID you will just get one protein of interest, and you can start from there. So, so this is a general format of a PDB file. So, as I said, that the microstate in a computer simulation basically a set of Ri and Pi. So, this Ri is nothing but x, y, z, x, y and z coordinates, and in PDB you exactly have that. You have the x coordinate, y coordinate and z coordinate for each of the atom. So, here in the at the top you have the title of the article, the journal where this particular work was published, the name of the authors, experimental parameters, the resolution at which the X-ray structure was deposited, and what is the functional class. In this case we are discussing about the protease. So now this molecule or this protein do have multiple amino acids. So this is amino acid number 1, which is a methionine. So in methionine we have this many atoms: nitrogen, C alpha, carbonyl carbon, carbonyl oxygen, C beta, C gamma, and so on. So for each atom I have x, y, and z coordinates. Then we have the second residue glue, and for each of these atoms we have x, y, and z coordinates. So if we put x, y, z coordinates of each atom, so this is atom xyz coordinate, xyz coordinate of atom 1, atom 2, atom 3, and so on and so forth. When we join them together, we basically get a 3-dimensional structure of the protein, and that is where we start from. So we start from here, and this is my initial microstates, the microstate number 1, and from here on I generate several other microstates to look how my protein conformation changes over time, and if I want to get the average over them, I take the time average or the ensemble average. So this is about the structure, but you can always calculate different thermodynamic quantity of the system. Okay, so in the protocol for MD simulation, the first step was initial coordinates. You had to start from a set of initial coordinates, and that you can get either from PDB, protein data bank, or if it is not available in PDB, you can make a crude set of coordinates by modeling it. The second step is a very important step, is called treatment of particle interactions, and for that we need to go back to our discussion yesterday. And if you recall, we said that the interparticle interactions, they are present or they are described by the potential energy of the system. So U, the potential energy, it contains the interparticle interaction information, and the U, what you written yesterday, was composed of several intramolecular and intermolecular interactions. I need to write it again to explain you the protocol number 2 in the MD simulation. So the bond was Ki by 2 Li minus Li0 square, where Li0 is the equilibrium bond distance, or the bond length. Then we had angle theta I by 2, K theta, the force constant, theta I minus theta equilibrium square, plus we had sum over all dihedral, and the expression was Vn by 2 1 plus cos n omega minus gamma, and then we had Lennard-Jones sum over I less than j for epsilon ij sigma ij Rij to the power 12 minus sigma ij Rij to the power 6, plus we had sum over I, sum over j, zi, zj by 4 pi epsilon 0 Rij. Here epsilon 0 is the dielectric constant of the medium, and epsilon 0, and epsilon is basically the energy depth. So this is having a unit of kcal per mole. So not to confuse epsilon 0 and epsilon. So this was the functional form of the U, which contains the interparticle interactions. Now, when we saw about the treatment of particle interactions, we need to look at these values, because Ki, Li, K theta, so all these quantities, they basically decide the interactions among the particles. So when the first term denotes a bond interaction, second term denotes angular interactions and dihedral interactions, the third term, and the last two terms indicate the intermolecular interactions. So in this whole expressions, as I said before, that Li is an instantaneous quantity. So Li varies. When the bond stretches, my Li could be 1.51 angstrom at some point. In another instant, my Li at time t plus delta t, it could be 1.54 angstrom. So Li is basically the instantaneous value of the bond distance. Likewise, theta I is the instantaneous value of the angle. But the other quantities like Ki, Li, K theta, theta I 0, not theta I, theta I 0, Vn, n, theta I, n, omega, epsilon, sigma, zi, zj, and epsilon 0, they are the fixed quantities. In other words, if you have a sp3 bond, sp3 carbon, sp3 carbon, their equilibrium bond distance, L equilibrium, is fixed. This L equilibrium distance is I think 1.53 angstrom, and likewise the K is also a known value. So these equilibrium values, they do not change. What changes is this instantaneous value of the bond. Likewise for angle also, the equilibrium angle of water is a fixed quantity, and around that equilibrium angle of water, the water molecule vibrate. So we can make a library where I have Ki, I have Li 0, I have K theta, I have theta I0, I have Vn n gamma, I have epsilon I epsilon, I have sigma, and then I make this library and I use this library whenever I see a molecule with CC bond. So, whenever I see a CC bond, I basically, instead of asking me to input the value, my algorithm, as soon as find carbon carbon sp3 bond, it will get this value from the library, and that library is called the force field. So, the force field is a very important term in computer simulation methods. So, force field basically contains the interaction parameters for various entities, for various atoms, and those force field parameters are kept in a library, and the algorithm basically looks for the similar bond and angle of the dihedral, and then gets those parameters from the library and use it for your system of interest. So, in the MD simulation protocol, the important step is choosing the right force field. So, when I say choosing the right force field, so the right depends on your system of interest. So, if you are simulating a membrane protein versus water soluble protein, then you need to choose different force field. Some force field are good for membrane proteins, some force field are good for water soluble proteins. So, so that's again the conceptual understanding of you about the system. So, once you understand your system, then you choose the right force field, and that force field will give you the better description of the system, and therefore you can reproduce the experimental data way better. So, here I written some names of certain MD simulation programs which basically can help you getting the different microstates. Some of them are free. GROMACS is a free software for molecular dynamics, and all of these software do have different force field, and it's up to you to choose the right force field for your system of interest. Then we need to, this is an important step, which is the treatment of solvent. So far, whenever I talked about generating the microstate, if you recall, I always put my protein in a box. So, if this is my protein, I put my protein in a box, and this we call a simulation box. So, simulation box is basically a dimension in which we put the protein. We put the protein at the center of the box. So, that protein has some boundary, and we put lot of water molecules around this protein to mimic the cellular environment. Since our body is having 60 to 70% water, we mimic that by putting the protein molecule in box full of water. So, now when you put water around the protein, there are two ways of describing the protein, the water. So, one way of describing the water is, as I drew, that I drew just as a sample as dot, but we can describe this water molecule as HOH. So, where my each dot here corresponds to this, where I have described the water molecule explicitly. So, this is the explicit description of water, explicit water, where I have HOH, and this water molecule would be able to make a hydrogen bond with another water molecule. It will be able to form a H bond with the protein peptide bond, and so on and so forth. So, this is the description of explicit water. You can have another way of describing water is that instead of describing the water explicitly, you assume that I have a dielectric medium here of epsilon 0.78. So, that is a implicit water model. So, in the implicit water, my water does not have the capacity of forming hydrogen bond with each other, neither it has the capacity of making hydrogen bond with the protein molecule. So, as you can see that when you have explicit description of the water, so you have much more molecules than molecules, and therefore the interactions to consider than implicit water, where I have just a dielectric medium. So, treatment of solvent is also important. So, if you are using a implicit solvent, you choose the dielectric constant of the medium. If it is water, you choose epsilon 0.78. If you are using the explicit water, then this is the explicit description of water, but then you have different model of water, which is beyond the scope of this course. So, about the different explicit water models. So, if you are using explicit solvent, then there are certain boundary conditions which you need to implement, and some of those boundary conditions are called periodic boundary condition, minimum image convention, and solvation sphere, which I will now describe one by